everyone, my name is Salma. I'm going to walk you through the Wonderland Chase problem statement. I am a site reliability engineer in Google Cloud. On the side, I like contributing to CodeJam problem development. I reviewed the statement of this problem as a non-native English speaker, and I also developed its solution analysis. Now, let's get started. Our problem is about Alice in Wonderland being chased by the Queen of Hearts. Our goal is to identify when Alice will get caught, or maybe she won't. Alice is trapped in Wonderland Labyrinth, which looks something like this. The labyrinth consists of a number of junctions. The junctions are connected to one another by bidirectional corridors. The starting position of both Alice and the Queen are known. The Queen starts by picking her first move. Her goal is to catch Alice in the smallest number of moves. The Queen tells the Herald her move, and the Herald announces it. Alice gets to make her move before the Queen does. She now knows the Queen's next move, so she can choose the optimal move to escape it, or at least maximize the number of moves until she is caught. After the Queen moves to the announced junction, they both keep taking turns to move. They can choose to either stay at the same junction or move through a corridor to another one, until Alice gets caught, or the Queen gives up. She will do so after 1 billion moves. The goal is to know how many moves it takes before the Queen catches Alice, if they both select moves optimally, or maybe the Queen will give up and Alice will be safe. I can't wait to see some of the creative approaches our finalists take to tackle this problem. Remember, there will be a live walkthrough of the solution on the live stream after the round ends. And don't forget to check out the analysis page for the problem after the round. Goodbye.
My name is Melisa Halsband. I work as a software engineer in the Google office in Dublin, Ireland. We're going to be going over the Wonderland Chase problem, so let's get into it. So this problem can be represented quite easily as a graph, where the junctions are represented as nodes and the corridors are represented as edges. The first thing to observe, quite trivially, is that the only way that the Queen has any hope of catching Alice is that they are both in the same connected component. If they are not, then Alice can just sit comfortably and watch YouTube, and then she will never be caught. So for the rest of the problem, we're going to consider that we're going to assume the Queen and Alice are in the same connected component, and we're only going to look at this component for the rest of the problem. So, an important observation to make now is that Alice will be always safe if she can get into a cycle within the graph. This is because even if the Queen is in the same cycle and just next to her, Alice can always go the opposite way. And sort of run in circles, Tom and Jerry style, and at the end of the chase, Alice will be tired, but certainly safe. So we're going to be using this later on. How are we going to solve the problem now? So something we can do is we're going to partition this graph into two subgraphs. A node is going to be considered to be in Alice's subgraph if Alice can get there first, meaning that she has a shorter distance from wherever she is, and if the node is at the same distance from Alice and the Queen, or the Queen is closer, then this node is going to be considered in the Queen's subgraph. We can find this out by performing a breadth search and just tagging the nodes with the distance from each of these ladies, like this, and so on and so forth. We actually can use the same traversal to find the connected components if we're interested in. Okay, once we have done this, we can look at Alice's subgraph. So obviously, for each node, we compare the distances, and whichever is smaller, we assign. And then we can look at Alice's subgraph on its own, and we can ask, are there any cycles in it? We can check this by performing now a depth first search in Alice's subgraph, or just by counting the nodes and edges. If there are as many edges as there are nodes or more, it means that there is at least one cycle, because this is a simple graph. Okay, if this is the case, then again, Alice is safe because as we have seen, if she can get into a cycle, she can stay there and be safe. So the second thing to observe is we need to check how many edges are there that have one end on the queen and one end on Alice's subgraphs. So something like this. So if there are at least two nodes that connect the two subgraphs, what we can observe is that there will be then at least one cycle that contains both the queen's and Alice's nodes, because Alice's subgraph is connected. It connects the two ends, and the same happens for the queen, and therefore we have now a cycle. If this happens, Alice is again safe, because she can reach any of the points in her subgraph before the queen can, so she can go to any part of her subgraph, and therefore she can get to any node in this loop, in this cycle that we found. Okay, so the last case to consider is if there are no cycles in Alice's subtree and if there are no more than one edge that connect the two graphs. In this case, actually, the things get a bit spicier for Alice because the queen has this strategy of getting into her end of this bridge node that connects the two graphs. And while Alice can get into any node into her graph, into her subgraph, by definition, because she has a shorter distance, then she will not be able to get into any of the queens because if that was the case, she would cross paths with the queen. And now Alice is effectively trapped in her own tree because the queen is sitting at the root of a graph that has no cycle, so this is a tree. And at each step, the queen will be closing in into Alice for going to whatever branch where Alice is, and eventually Alice will be caught. So what can Alice do in order to maximize the chase, and in the hope that the queen tires and gives up the chase? She will have to go to the furthest away leaf in her subtree. And which is this leaf? Well, we have calculated this already when we calculated the distance from the queen to each of the nodes in the graph. So we know which will be the furthest that the queen would have to traverse in order to corner Alice into a leaf. So this is what Alice will have to do in order to maximize the chase. And this number would have to be multiplied by 2 because both Alice and the queen take turns, and that's the result of the problem. I hope you have enjoyed it as much as I did.